You are made of atoms: carbon, hydrogen, oxygen, nitrogen. The chair beneath you, the air you breathe, the stars burning in the night sky. Everything you've ever touched, seen, or experienced. Everything humanity has ever discovered across 400 years of modern science. All of it, every planet, every galaxy, every particle in our telescopes, represents less than 5% of the universe. 5%. What if I told you that 95% of reality is completely invisible to us? That the cosmos is dominated by two mysterious entities we cannot see, cannot touch, cannot directly detect with any instrument ever built. That the universe you think you know is merely a thin foam floating on an invisible ocean. In 1933, a Swiss astronomer named Fritz Zwicky discovered something impossible while studying a cluster of galaxies 320 million light years away. The galaxies were moving far too fast. According to every law of physics, they should have torn themselves apart. But they didn't. They were being held together by something we couldn't see. Something with 5 times more mass than everything visible. He called it Dunkelmaterei, dark matter. 60 years later, astronomers discovered something even stranger. The universe isn't just expanding, it's accelerating. Being pushed apart by a mysterious force we call dark energy, an anti-gravity that fills the emptiness of space itself. Today, we journey through evidence that challenges everything we thought we knew about existence. From spinning galaxies to the cosmic web itself, from the echo of creation to the ultimate fate of everything. Prepare yourselves. We begin the discovery, the problem in the Coma Cluster. The year is 1933. The place, Mount Wilson Observatory, California. Fritz Zwicky, a brilliant and notoriously difficult Swiss astrophysicist, points one of the world's most powerful telescopes toward the Coma Cluster, a dense congregation of over 1,000 galaxies bound together by gravity. He measures their velocities, how fast they orbit around each other. The numbers don't make sense. These galaxies are moving at speeds exceeding 1,000 kilometers per second. By every calculation, based on the visible matter within the cluster, this is impossible. It's like watching a carousel spin so fast its horses should fly off into space. Yet somehow they remain locked in perfect orbit. Zwicky performs the calculations again and again. The conclusion is inescapable. There must be approximately 400 times more mass in the Coma Cluster than we can actually see. An invisible ocean of matter, generating gravity, but emitting no light whatsoever. The scientific community largely ignores him. It seems too radical, too strange. 40 years have passed. The rotation problem. In the 1970s, astronomer Vera Rubin at the Carnegie Institution points her instruments toward spiral galaxies. She's measuring rotation curves, how fast stars orbit around galactic centers at various distances. Basic physics predicts a clear pattern. Stars farther from the center should orbit more slowly, just as Neptune takes 165 years to circle the Sun, while Mercury completes its orbit in just 88 days. But that's not what Rubin observes. Stars at the outer edges of galaxies are moving just as fast as those near the center. In galaxy after galaxy, the same impossible pattern repeats. Andromeda, our nearest large galactic neighbor, shows it. The Triangulum galaxy shows it. Every spiral galaxy Rubin examines displays the same flat rotation curve. The implications are staggering. Something invisible is holding these galaxies together. Something with enormous mass, extending far beyond the visible disk of stars and gas. Dark matter isn't just in the Coma cluster, it's everywhere. It surrounds every galaxy like an invisible halo, 10 times more massive than all the stars we can see. The evidence forces astronomers to confront an uncomfortable truth. We live in a universe where the visible is the minority, where light-emitting matter is merely the tip of an invisible iceberg. But what is this dark matter? Why can't we see it? The answer lies in the nature of matter itself. Ordinary atoms, protons, neutrons, electrons interact with light. They absorb photons, emit photons, reflect and refract electromagnetic radiation. That's how we see everything. But dark matter doesn't play by these rules. It doesn't interact with light at all. No absorption, no emission, no reflection. Photons pass through it like ghosts through walls. Yet it has mass. It generates gravity. And gravity is what shapes the cosmic architecture of everything. Think of it this way. Imagine you're in a completely dark room with invisible people moving around you. You can't see them, can't hear them, can't detect them with your senses, but you can feel their gravity. You notice objects moving, feel yourself being pulled and pushed by their presence. That's what we're experiencing with dark matter, a gravitational presence without a visual signature. By the 1980s, the hypothesis was gaining traction, but astronomers need more evidence. They need to see dark matter's gravitational fingerprints across the cosmos. They find them in the most spectacular way imaginable. Gravitational lensing. Einstein's general relativity predicts that massive objects bend spacetime itself. Light follows the curvature of spacetime, meaning massive objects can act as cosmic lenses, bending and distorting the light from objects behind them. In 1979, astronomers discovered twin quasar, what appears to be two identical quasars separated by just 6 arcseconds in the sky. But they're not twins. They're the same quasar. Its light split and bent around a massive galaxy positioned between us and the quasar. The galaxy's gravity has created a cosmic mirage. Astronomers realize they have a new tool. By studying how light bends around galaxy clusters, they can map the distribution of mass, all mass, visible and invisible. What they discover is stunning. When they map gravitational lensing around galaxy clusters, The mass distribution extends far beyond the visible galaxies. Vast halos of invisible matter dominate the structure. In some clusters, they can actually see the dark matter distribution mapped out in the distorted, stretched images of background galaxies, like looking at funhouse mirror reflections caused by invisible glass. The evidence is no longer circumstantial. Dark matter isn't just a hypothesis to explain unexpected motion. It's a real, measurable component of the universe that shapes the path of light itself. But this represents just one piece of a much larger puzzle, because in 1998, astronomers were about to discover something even stranger. Something that would force us to confront an entirely new mystery in the cosmos. The universe is accelerating, accumulating evidence, observable signatures. The year is 1998. Two independent teams of astronomers, the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, are racing to measure the universe's expansion rate by observing type Ia supernovae in distant galaxies. These stellar explosions are nature's perfect standard candles. They always explode with the same intrinsic brightness, allowing astronomers to calculate their distance with precision. By measuring how much their light has been redshifted, stretched by cosmic expansion, they can determine how fast the universe was expanding at different epochs in cosmic history. Both teams expect to measure the universe's deceleration. Gravity should be slowing the expansion, like a ball thrown upward, gradually losing speed. The data tells a different story. The distant supernovae are dimmer than they should be, farther away than predicted. The only explanation: the universe's expansion is accelerating, slowing down, speeding up. The announcement sends shockwaves through the physics community. It violates intuition. Gravity is attractive. It should pull things together. Slow expansion. What could possibly push the universe apart with ever-increasing force? The answer requires us to resurrect an idea Einstein once called his biggest blunder. In 1917, Einstein added a term to his field equations, the cosmological constant, representing an inherent energy density in empty space itself, a kind of anti-gravity to keep the universe static, matching the astronomical observations of his era. When Edwin Hubble discovered cosmic expansion in 1929, Einstein abandoned the cosmological constant, believing he'd made a fundamental error. But the 1998 supernova results suggest Einstein was right the first time, just for the wrong reasons. Empty space does have energy, and that energy, now called dark energy, is pushing the universe apart. The measurements are refined. The acceleration began approximately 5 billion years ago. Before that, gravity dominated, slowing expansion. After that point, dark energy took over, driving galaxies apart at ever-increasing speeds. The numbers are precise. Dark energy comprises roughly 68% of the universe's total energy content. Dark matter accounts for 27%. Ordinary matter atoms, stars, planets, us, makes up just 5%. We live in a universe dominated by the invisible, the cosmic microwave background. But here's where the evidence becomes overwhelming. In 2003, NASA's Wilkinson Microwave Anisotropy probe began mapping the oldest light in the universe, the cosmic microwave background radiation. This is the echo of creation itself. Light was released 380,000 years after the Big Bang, when the universe first became transparent. It's been traveling through space for 13.8 billion years, cooling from thousands of degrees to just 2.7 Kelvin above absolute zero. The WMAP data reveals tiny temperature fluctuations in this ancient light, variations of just 0.0001 degrees. These fluctuations are the seeds of cosmic structure, quantum variations inflated to cosmic scales by the Big Bang itself. But here's the remarkable part. The pattern of these fluctuations tells us exactly what the universe is made of. The physics is complex, but the principle is elegant. The early universe was a plasma of matter and radiation, oscillating like sound waves, acoustic oscillations in the cosmic fluid. The scale of these oscillations depends on the universe's composition. Dark matter, which doesn't interact with radiation, creates a characteristic signature in the oscillation pattern. Dark energy affects the geometry of space-time itself, changing how we observe these fluctuations. When cosmologists analyze the data, the results confirm the supernova findings with stunning precision. The universe is 68.3% dark energy, 26.8% dark matter, 4.9% ordinary matter. The uncertainty is less than 1%. Multiple independent lines of evidence, galaxy rotation curves, gravitational lensing, supernova observations, the cosmic microwave background, all point to the same conclusion. But this represents just one piece of a much larger puzzle, hidden in the cosmic web itself. Deeper implications. In 2006, astronomers announced one of the most remarkable observations in cosmological history. They've been studying the bullet cluster, actually 2 galaxy clusters that collided 150 million years ago at speeds of 4,500 kilometers per second. When galaxy clusters collide, they provide a natural experiment. The visible matter gas between galaxies slams together and gets heated to hundreds of millions of degrees, emitting X-rays we can detect. But dark matter, interacting only through gravity, passes right through. Using gravitational lensing, astronomers map where the mass actually is. The results are spectacular. The X-ray emission showing where the visible matter ended up, is separated from the gravitational lensing signal, showing where most of the mass actually resides. The dark matter halos passed through each other like ghosts, while the visible matter stayed behind. This observation rules out alternative theories. Some physicists had proposed modifying the laws of gravity rather than invoking dark matter. But modified gravity can't explain the bullet cluster. The mass is spatially separated from the visible matter. Dark matter must be real, physical particles. But what particles? The search intensifies. Physicists propose candidates: WIMPs, weakly interacting massive particles; axions, sterile neutrinos; deep underground laboratories around the world: Xenon in Italy, Lux, CPLIN in South Dakota, PandaX in China, try to detect dark matter particles colliding with ordinary atoms. Decades pass. Despite increasing sensitivity, direct detection remains elusive. Dark matter continues to hide, interacting so weakly with ordinary matter that even kilometers of rock and millions of kilograms of detector material cannot capture a single definitive collision. Meanwhile, cosmologists map the large-scale structure of the universe with unprecedented detail. The Sloan Digital Sky survey catalogs positions of over 1 million galaxies. When astronomers plot these positions in three-dimensional space, a stunning pattern emerges. Galaxies form a cosmic web. Long filaments of matter stretching across hundreds of millions of light years, intersecting at dense nodes, galaxy clusters. Between the filaments, vast cosmic voids, regions nearly empty of galaxies. Computer simulations of structure formation, incorporating dark matter and dark energy, reproduce this cosmic web with remarkable accuracy. Dark matter creates the gravitational scaffolding. Ordinary matter follows, flowing along dark matter filaments like water following channels carved in stone. The most remarkable discovery involves the early universe itself. In 2013, the Planck satellite produced the most detailed map of the cosmic microwave background ever created. The data allows cosmologists to rewind cosmic history, determining conditions mere fractions of a second after the Big Bang. The evidence suggests something extraordinary. Dark energy may not be constant. Its density might change over cosmic time. Some measurements hint at what physicists call phantom energy, dark energy, that actually increases in density as the universe expands. If true, the implications are profound. The standard model of cosmology, lambda CDM, named for the cosmological constant, lambda, and cold dark matter, CDM, may need revision. Dark energy might be something more complex than Einstein's cosmological constant. Something dynamic. Something that could determine the ultimate fate of the universe itself. The evidence extends beyond observation into the realm of cosmic destiny. The big picture, theoretical framework. let's step back and consider what we know. Dark matter and dark energy are not just astronomical curiosities. They are fundamental components of reality, shaping the universe's past, present, and future. Dark matter provided the gravitational seeds for structure formation. Without it, the tiny fluctuations in the early universe couldn't have grown into galaxies. Ordinary matter alone, buffeted by radiation pressure, couldn't have collapsed fast enough. Dark matter, immune to radiation, created gravitational wells that ordinary matter fell into. Think of it this way: dark matter is the invisible scaffolding of cosmic architecture. Galaxies are ornaments hanging on a dark Christmas tree we cannot see. But what is dark matter made of? The leading hypothesis involves WIMPs, particles with mass between 10 and 1,000 times that of a proton, interacting only through gravity and the weak nuclear force. They would have been produced in enormous quantities during the Big Bang, then cooled as the universe expanded, forming the halos we observe around galaxies. Supersymmetry, a theoretical extension of the standard model of particle physics, naturally predicts such particles. The lightest supersymmetric particle, potentially a neutralino, could be stable, massive, and weakly interacting. Precisely the properties dark matter requires. But despite searches at the Large Hadron Collider and direct detection experiments, no WIMP has been conclusively identified. Alternative candidates emerge. Axions, hypothetical particles proposed to solve a different problem in quantum chromodynamics, could also comprise dark matter. They would be extraordinarily light, about a billionth the mass of an electron, but produced in such enormous quantities that they dominate the universe's mass budget. Then there are primordial black holes formed in the early universe rather than from stellar collapse. Could dark matter simply be vast numbers of small black holes, too small to detect individually, but collectively providing the necessary gravitational influence? Each hypothesis makes predictions. Each can be tested. The search continues. Dark energy presents an even deeper mystery. The simplest explanation is Einstein's cosmological constant, a fixed energy density inherent in space-time itself. Quantum field theory predicts such a vacuum energy should exist. But when physicists calculate its expected value, they get an answer 10^120 times larger than observed. 120 orders of magnitude. This is what physicists call the cosmological constant problem, and it represents the worst theoretical prediction in the history of physics. Something is profoundly wrong with our understanding. Either quantum field theory is missing something fundamental, or there's a mechanism suppressing vacuum energy that we don't comprehend. Alternative theories propose quintessence, a dynamic scalar field permeating space, changing over time. Unlike the cosmological constant, quintessence could vary, potentially explaining why dark energy's density appears fine-tuned to dominate precisely in our cosmic era. This forces us to reconsider fundamental assumptions about the nature of empty space, the vacuum, and the relationship between quantum mechanics and gravity. Future implications. The next decade promises unprecedented insights. The Vera C. Rubin Observatory in Chile, operational since 2025, is conducting the legacy survey of space and time, cataloging billions of galaxies with unprecedented precision. By mapping gravitational lensing across the entire sky, it's creating the most detailed map of dark matter distribution ever produced. The European Space Agency's Euclid mission, launched in 2023, is measuring cosmic acceleration with exquisite accuracy, determining whether dark energy is truly constant or changes over time. NASA's Nancy Grace Roman Space Telescope, launching soon, will conduct the largest supernova survey in history, measuring cosmic expansion across billions of years of cosmic time. Meanwhile, dark matter detection experiments reach new sensitivities. The next generation of detectors, using liquid xenon targets cooled to 100 degrees C in deep underground facilities, will probe interaction cross-sections 1,000 times smaller than current limits. If dark matter is WIMPs, we're approaching the threshold where detection becomes unavoidable. If experiments continue to find nothing, physicists will be forced to abandon WIMPs and pursue more exotic alternatives. The Large Hadron Collider continues to search for supersymmetric particles, pushing into higher energy regimes where new physics might hide. Theoretical physicists explore increasingly radical ideas. Could dark matter be composed of dark atoms, forming dark molecules and dark stars in a parallel dark sector? Could there be entire dark galaxies, invisible cosmic structures permeating our own Milky Way? Recent breakthroughs suggest we're approaching critical junctures. In 2023, researchers analyzing pulsar timing arrays announced potential evidence for gravitational waves from the early universe ripples in space-time that could carry signatures of dark matter's nature and distribution during cosmic dawn. Advanced telescopes, like the James Webb Space Telescope, observe the earliest galaxies, formed just 200 million years after the Big Bang. Their properties, masses, sizes, abundances depend critically on dark matter's behavior during structure formation. Any mismatch between observation and prediction could revolutionize our understanding. The most profound question remains: are dark matter and dark energy related? Some theories propose their different manifestations of a single phenomenon, a modification of space-time itself at cosmic scales. Others suggest they're completely independent, arising from different physics. The answer could unify our understanding of the cosmos or reveal even deeper mysteries. What we discover in the next decade will shape physics for centuries. The ultimate questions. Now we arrive at the most mind-bending implications. If dark energy is constant, a true cosmological constant, the universe's fate is sealed. Cosmic expansion will accelerate forever. In trillions of years, galaxies outside our local group will recede beyond our cosmic horizon, their light redshifted into oblivion. The observable universe will shrink. Eventually, in 100 years or more, stars will exhaust their fuel. Black holes will evaporate through Hawking radiation. The universe will approach a state of maximum entropy, the heat death, where no energy differences exist and nothing can ever happen again. But if dark energy is phantom energy, growing stronger over time, the fate becomes more dramatic. In this scenario, dark energy's repulsive force increases without limit. First, galaxy clusters unbind, then galaxies themselves. Eventually, solar systems disintegrate as dark energy's pull overcomes gravitational bonds. Finally, atoms themselves tear apart. Physicists call this the Big Rip. It could occur as soon as 22 billion years from now, just 35 billion years after the Big Bang. The universe wouldn't fade away. It would tear itself to pieces in a crescendo of cosmic violence. The most profound implications emerge when we consider the anthropic principle. Why do dark matter and dark energy have precisely the values they do? Why is dark energy's density so perfectly balanced to allow structure formation, and then dominate precisely when complex life could emerge? If dark energy were slightly stronger, it would have prevented galaxy formation entirely. The universe would remain a diffuse gas, forever expanding. No stars, no planets, no life. If slightly weaker, the universe might have collapsed in a big crunch billions of years ago. The parameters seem fine-tuned. This bothers physicists deeply. One explanation: the multiverse. Perhaps countless universes exist, each with different values of dark energy, dark matter, and fundamental constants. We observe these particular values because only universes with such values produce observers. It's selection bias on a cosmic scale. We couldn't exist in universes where conditions were different. But this explanation troubles many scientists. It's unfalsifiable, potentially beyond science's reach. Yet the alternative, accepting fine-tuning as brute fact, seems equally unsatisfying. Another possibility: we're missing something fundamental. Perhaps dark energy and dark matter are emergent phenomena, arising from deeper physics we haven't discovered. Perhaps space-time itself is not fundamental, but emerges from underlying quantum information. String theory predicts extra dimensions beyond the 3 spatial dimensions we experience. Could dark energy and dark matter be gravitational effects from these higher dimensions, leaking into our observable universe? loop quantum gravity suggests space-time is discrete at the smallest scales, quantum foam, where geometry itself fluctuates. Could dark energy arise from these quantum properties of space? The questions multiply. Some physicists propose we're living in a false vacuum, a metastable state of space-time that could suddenly decay to a lower energy state. Such a decay would propagate at the speed of light, fundamentally altering physics in an expanding bubble of new vacuum. It could happen tomorrow. It could happen in 1,000 years. We have no way of knowing. The existence of dark matter and dark energy forces us to confront our ignorance. We understand 5% of the universe. The rest remains a mystery. But here's the remarkable part. We know that we don't know. We've identified our ignorance with precision. We've measured the invisible. We've mapped what we cannot see. That's not failure. That's the triumph of the scientific method, the willingness to follow evidence wherever it leads, even when it reveals our own limitations. We began this journey with a simple observation: galaxies spinning too fast. We've traveled through decades of evidence, rotation curves, gravitational lensing, the cosmic microwave background, colliding clusters, the cosmic web itself. Every measurement, every observation, every independent line of evidence points toward the same remarkable truth. Universe is vast, stranger, and more mysterious than we ever imagined. We are surrounded by the invisible. We are embedded in a cosmic ocean of dark matter, pushed apart by dark energy's inexorable force. Yet, we've learned to see the unseeable. Through gravity's signature, through light's distortion, through the echo of creation itself, we've mapped the invisible architecture of reality. The current scientific consensus is clear. Dark matter and dark energy are real, fundamental components of the cosmos, but their ultimate nature remains unknown. We've identified the mystery, measured its properties, traced its influence across 13.8 billion years of cosmic history. But we still don't know what they are. That's where we stand, at the boundary between knowledge and mystery. With tools powerful enough to detect the unseeable, but not yet sophisticated enough to identify it. With theories elegant enough to explain the observable, but incomplete enough to leave the fundamental questions unanswered. The next chapter is being written now, in laboratories buried beneath mountains, in telescopes orbiting above Earth's atmosphere, in the minds of physicists and astronomers pushing toward understanding. What we discover will reshape our place in the cosmos, will reveal whether we live in a universe destined for heat death or cosmic rip, in one universe or many, in a reality where space-time is fundamental or emergent. The universe has humbled us. Show us that everything we see, everything we've ever touched or known, represents just a tiny fraction of existence. But it's also shown us something profound about humanity itself. We can know things beyond our senses. We can understand the invisible through reason and evidence. We can measure what we cannot see and map what we cannot touch. 5% visible, 95% mystery. And yet, we continue to search, continue to question, continue to push toward understanding.